Thanks. Um, so yeah, I do a flavor direct imaging. I specialize in the mid-infrared ground-based observations, so just not just mid-infrared, but just not JWST. Um, okay. Um, so direct imaging is basically what you're doing is you're measuring the photons directly emitted from hot and massive planets. These photons, because they're emitted directly from the planets, directly access the planet's atmospheres. And in general, we typically observe these planets in near-infrared wavelengths, so about 1 to 3 microns. Um, but because of the nature of direct imaging, what you're really sensitive to, this is a mass and orbital radius plot, what you're really sensitive to are really hot, large planets far away from their host star. Um, but so my work is basically hoping to expand this parameter space, basically to older and colder planets. So what that means is that you're actually accessing lower mass planets as well. Um, and again, so the science goals, we want to directly image these planets in the mid-infrared using M-band imaging. Specifically, I use the Keck telescope with a NERC2 imager. And so with a spectrum or a photometric data point at M-band, you can actually derive and model a variety of atmospheric properties, such as the C to O ratio, disequilibrium chemistry, and cloud coverage. So on the right here, we have a spectrum of the planet 51 Area B. And then on the very right, we have this M-band data point. And you can see that it's actually not a really well-constrained data point. The error bars are pretty large. But what's interesting is that this data point can actually explain a very wide range of different models. As in, if this data point was much better constrained, it would, if the data point was much better constrained, it would have much more constraining power on the actual properties of the planet. Um, and this is also really important because cooler planets are typically just more accessible at long wavelengths because the SED just peaks at long wavelengths. Um, so another example of this, just last year, one of the first direct imaging detections with JWST was EPS-NDB. So this is actually a very widely separated target detected by JWST at 10 microns, right? But what I wanted to point out was that, so the black here is the JWST data points. But I wanted to point out that they actually had ground-based measurements for this particular target at 4 microns, and they set an upper limit in 2008 with this 4 micron data point. But if they instead imaged at M band or slightly longer wavelengths from the ground, right here, they actually would have a lot more constraining power in the properties of this planet. And it would have gotten a much better spectral fit, even if they set an upper limit. Um, And so in general, so we typically like to use this term called contrast in direct imaging. Contrast is just the host star to planet flux ratio. Um, and so contrast is typically a lot better in M-band for very low temperature planets. Here on the right, we have just, I use two models, just the Sonora Elf Owl planet models and the Phoenix stellar models for a sun-like star with a Jupiter-like planet, right? And you can see that M-band is significantly brighter than the JHK near-infrared wavelengths that we're typically used to. L prime is also good, as you can see, but it doesn't have the same spectral information that we're looking for. L prime and L are much wider band passes. And so what's also important to note here is kind of the shallowness of this curve, right? So what that means is that because this slope is relatively shallow, even marginal improvements in your contrast can vastly increase your sensitivity and what you're able to detect. And so some of the good things about M-band is that, again, exoplanets are generally brighter in M-band than other wavelengths, cooler ones especially. But actual observing benefits, like the AO system just performs better. The atmospheric coherence timescale is longer, so that means that your PSF is just much more stable throughout the night. But the main reason why people don't choose M-band is because there are certain problems associated with it. Um, and so when you have your typical JHK, L and L prime bands, and you can see they all occupy this particular atmospheric window. This is the transmission of the Earth's atmosphere versus wavelength. Each of the bands occupy a specific window in the Earth's atmosphere. They have M band all the way out here, and you can see this atmospheric transition window is actually pretty messy. And this messiness comes from water vapor and absorption features. Um, the main issue, in addition to this, is that you're actually seeing through the black body emission from the atmosphere itself. So you're directly accessing, the black body emission of the atmosphere and your telescope and your instrument. And what you're trying to do is basically trying to look at a faraway flashlight, like the star, through another flashlight. So it makes it pretty hard. And so you're probably thinking now, why don't we just use J2ST for a lot of these observations? And I think the really simple answer is that you just have much larger apertures in the ground. So you just get higher resolution as you get to longer wavelengths. And yeah, obviously as you increase your wavelength, this advantage increases drastically as well. Not only that, but it's just easier to get observation time. And if you want to do anything like a variability study or orbital monitoring, you should do it from the ground. And I think a rule of thumb is that if you can do an observation from the ground, or if you can do your particular science from the ground, then there's no reason to do it with J2ST. So circling back, so this is kind of what a sky image looks like. This is a sky image with no target in this field of view. This is literally just pointing the telescope and taking an image of a blank patch of sky just to see what the thermal background looks like. And so some of the properties of the thermal background is that it's quasi-static, so it doesn't change that much over time. It's not totally random. You see these large-scale features. It definitely has some kind of structure. This background is also dependent on the atmospheric conditions at the time. But I think, importantly, there's not a super clear origin as to where this comes from. And so kind of what people expect right now is that the thermal background comes from three primary sources. How much each of these sources contributes to the thermal background is kind of the big question that people wonder. So we have terrestrial water vapor, as I was talking about before, but you also have these internal instrumental sources, and you have dust on the optics, right? Um, and so what's important to know is that two of these things are within our control, right? These are systematic things that we can control for. But one of them is something that's out of our control. So in our post-processing, we better do our best to deal with all these systematic issues. And so in a typical direct imaging workflow, this is not in the thermal infrared, but just a general direct imaging workflow. You kind of start with your observations, use angular differential imaging, which I'll explain in a second. You take your observations, you align them in a stack, and then you subtract the PSF in each frame using your Loki or PCA or whatever your favorite algorithm is. And then you rotate the frames to align the planet signal, and then you median the stack. And then eventually you get these nice direct imaging you get these nice images of your planet with the star subtracted. And so I'll use this technique called angular differential imaging. I'm not going to explain it. I'm not going to explain it in detail, but the most important part that angular differential imaging does is that it separates your planet signal from your star signal, right? So it adds this rotational element so that you can separate out the planet signal from the actual PSF. And so this concept of the signal separation I'll come back to later, but that's important. And so when dealing with the thermal background, there's actually been a few studies done on how to actually deal with the thermal background. One of the first ones was Galashay in 2011. But basically the whole idea is that you kind of take your point source and then you dither it around your frame. And then you use reference frames where the point source was previously to minimize the background variation in your target frame. And the main assumption here is that the thermal background is similar between frames, or similar enough that when you take subsequent frames that you can do a least squares stack and kind of subtract it. And so when you add this background subtraction, how this adds into your workflow, you have your observations using angular differential imaging, and then you add this dithering element to it as well. And then you subtract your thermal background before doing anything else. Then you align your frames in the stack and you go through and again, you get your planet signal out at the very end. And so we went about doing this. The target that I was particularly interested in is ABR Riga. ABR Riga is just a Urbig AE star. It has a forming protoplanet and a very extended disk. It's a very large disk. And so this is a very, very well-studied system. But most of the data in the near infrared has been just obtained in JHK and L bands. I don't believe that there's a data point in M band quite yet. So the main goal of my campaign was to to get an M band data point on this forming protoplanet. And so this is we took 4 half nights worth of data last year. And again, we were using NERC2 on Keck. We had about 4 hours of integration time. We also took sky frames in between dither positions. And so here's like an example sequence of one of the first data sets we were using. And so you see that you can see the thermal background very clearly, and we're dithering our point source throughout the frame. And so I made this video and then I stared at it for a very, very long time. I was like, basically trying to understand what was going on with the thermal background, because you see it's kind of like jiggling around, it's moving, there's small variations. But if you look really, really, really hard at this video, you can see that it's actually moving in like kind of like a deterministic way, like it's kind of shifting or sliding. And basically what I found is that it's actually rotating, right? So what you're actually seeing, so what we realized that we were seeing is that we're seeing the de-rotator mirror in the optical path. And so the de-rotator is a particular optic that basically just keeps your image in a particular orientation for your observation throughout the night. The de-rotator basically just orients the frame and it rotates the image within the focal plane. But what's important is that the de-rotator, specifically on NERC2, de-rotates using a translation and a rotation. So it wasn't abundantly clear, but if you take this translation and rotation of the de-rotator and you apply it to your frames, and basically you take this transformation into your reference frame, you transform it into the de-rotator reference frame, you start to track this mysterious thermal background signal. And so I'll play it one more time. But yeah, so you're starting to see that the background signal is now you're kind of like mapping out this thermal background on the de-rotator. And so in another set of observations, we actually set the de-rotator to a stationary position to check to see that this is indeed the de-rotator. Normally in ADI mode, the de-rotator tracks the pupil of the telescope for angular differential imaging. So in this case, since we said it's a stationary, the pupil is rotating, and then you see that the thermal background no longer rotates. It does have all these jiggles, which are also interesting. And so the question is that basically is that the atmosphere, or is that something else on the bench? And so in this particular sequence, we kept the adaptive optics system in a closed loop. And we took one more short sequence where we actually, again, de-rotator in stationary mode, but this time we took open loop data. So the adaptive optics system is off. And we see that most of the jiggling goes away, right? So we actually see that this thermal background is being modulated by the adaptive optics system and the de-rotator. And a lot of the variation that we had previously assumed to be the atmosphere was actually due to these systematic effects. And so if you take this de-rotator signal and you stack it and you remove the PSF, you could see that this is kind of like a de-rotator map of what we are seeing. This is an entire sequence throughout the night. And so what the de-rotator is an extra signal that rotates underneath our data. It rotates at a different rate than our planet. And so just like ADI, we need to separate out the signal in our post-processing. We need to add some extra step in order to remove this signal. And so we think that the de-rotator is just likely dust. We think the thermal signal is pretty much just coming from dust on the mirror surface of the Keck. Sorry, we think that the emission is primarily dust on the surface of the mirror of the de-rotator. It also could be imperfections of the optics. Um, so this is a diagram of the Keck II AO bench, and you can see that the de-rotator is actually really close to the first focus or the first focal point of the telescope. And what that means is that if you imagine yourself as a piece of dust emitting as a point source on the surface of this mirror, you'd be most readily imaged at the end of the focal plane. And so the de-rotator is a necessary optic. You'll find it on pretty much every single alt-az telescope that has instruments that are not directly mounted to the telescope. Um, but yeah, so how do we kind of get rid of this? And so going back to what we were talking about before, low-key and PCA techniques, they're basically just least squares noise minimization techniques. What you do is you have a linear combination of basis frames that minimize the residual signal in your target frame. Your basis signal or your basis frames represent all the information that you're feeding to your algorithm. So you need to actually construct your basis to remove the background using all the information possible. And so because the de-rotator signal is rotating at a different rate than everything else in the system, it's not accounted for in these like standard background subtraction techniques that people were using before. And so your typical basis just looks like this, right? You have your dithered frames, just like background Loki. You're using the other frames that aren't your target, and you're using those as your basis. But what I did instead was that you create this new basis, adding de-rotator frames. These de-rotator frames are transformed into the de-rotator reference frames. And then you also add in these extra sky frames, which we took in between dither positions so that they actually match the angle of the de-rotator relatively closely. And then so using this new basis, you again construct an optimal linear combination of this to subtract the background signal. And you construct a background subtraction map to create a background subtracted image in the end. And after that, you can just do your regular least squares PSF subtraction. And so finally, applying this to our data. So this is the final data set that we got. Again, we had 4 half nights of data. The red there is actually where the target is supposed to be. And so we don't see anything, unfortunately. But we do see this like northern prominent, this northern spiral arm, which is pretty prominent. But we don't see too much of the extended disk. And basically, we think this is just because we're not reaching the contrast limit. So this planet was expected to be between 10 to the minus 6 and 10 to the minus 5 at M band, and we're reaching somewhere closer to 2 times 10 to the minus 5. So we're not quite at the limits to see the planet, but we do see that we are seeing a relative improvement by subtracting our background. Our final limiting contrast is about 2 times 10 to the minus 5, which is probably the best upper limit that anyone's put so far in the system. And I guess a couple other notes about this is that we generally do better further away from the host star, so the background subtraction works better. That's probably because the speckle we're speckle dominated close into the star, but background dominated as we move further. And yeah, so we're not seeing the planet, but this was a really interesting study. So another thing I wanted to note was that ground-based mid-infrared imaging, we had this beautiful space telescope, but there is going to still be a lot of activity on the ground for ground-based mid-infrared imaging. And so we have ERIS on the VLT, which is a 1 to 5 micron imager. Scales is going on Keck sometime next year, which is again a 1 to 5 micron IFS. And in the far future, on 30-meter class instruments, the first light instruments are slated to be mid-infrared imagers, taking advantage again of the high angular resolution that you get from the ground. And so in conclusion, so we kind of just did this deep dive on the thermal background systematics on this Keck data, and we developed a method for removing this thermal background. We kind of unveiled a huge part of this mystery background was really just the de-rotator plus the adaptive optics system. And I also want to note that we actually see this very, very similar thermal background features on other instruments. So there are a couple other studies done at the VLT, La Palma, on other telescopes that reach out into the mid-infrared. And you see that they have very, very similar features. But again, the specifics depend on the exact optics of your of your optical bench. And so not only that, but the de-rotator affects all instruments downstream the AO bench. Um, so this is like an important study for at least the Keck community. And so I do want to, I do want to emphasize that this is a specific study just for the Keck II AO system. But I think the main takeaway that I want to communicate here is that, you should always consider and treat all systematics carefully. Otherwise, you could reduce performance and bias data. But yeah, that's it.
All right, thanks so much, Jake. Any questions? Again, you can use the hand raise tool. You can put something in the chat. All right, so I do see one question from Madeline Broom in the chat. So just a naive question, why not clean the dust, or does it just return too fast?
Right. Yeah. So they have tried cleaning the dust. Yeah, the surface of the de-rotator is actually huge. They have tried cleaning the dust. It doesn't come off very easily. Um, yeah, so they've tried. It just doesn't work, and they're too afraid to do anything more invasive. And not only that, but there are a lot of like other previous data sets that have the dust on it, so you still need this technique.
Yeah, I imagine not wanting to futz with the equipment is probably yeah, true. All right. Thanks. Okay, Heis, you have a question.
Yeah, I was wondering if it was possible to not use the de-rotator in these observations. Like there are direct imaging, especially angular differential imaging, I think where you don't use the de-rotator so that the planet moves on the camera. So is that an option here in the N-band or not?
Yeah, so we did actually, I didn't mention it, but in this data set, this particular data set, we did try turning off the de-rotator. And so again, if you turn off the de-rotator, your PSF rotates on sky. But when I was talking to the Keck AO folks, what actually happens is as your PSF is rotating, they're using a different reconstruction matrix for the AO system for a different angle of the de-rotator. And what that means is that like the reconstruction matrices are built like using calibration sources and stuff. Each reconstruction matrix is slightly different, so your PSF is slightly different at each angle. And so when you eventually do the final de-rotation and stack, the PSF variation, especially close in, is a lot worse. So you suffer a lot from the speckle noise. And basically the trade-off of freezing the background versus the speckle noise in the PSF isn't as good as we thought. And this data set is clearly worse than the rest of them. So yeah.
Okay, makes sense. Yeah.
All right, thanks, Heis. All right, with that, let's thank Jake again for an excellent talk.